Okay, to hopefully clarify this notation that I kind of messed up before. This is a solution. This means if we let y1 equal e to the t cosine squared of 2t, y2 equal negative square root of 2 over 2 e to the t sinus square root of 2t, that plugged in here for y1 and y2 is going to give us a solution. But this is just one of the two linearly independent solutions of our system. Okay, we got two equations, we got a y1, y2. We expect two linearly independent column vectors. So if we do the same thing, let this be y1 and this be y2, it's also going to be a solution. Now if we form a matrix of these two, it's going to look something like this. It's going to be, here's our first column, and here's going to be our second column. We take the determinant of that, that's going to be our Wronskian. We're going to prove it's non-zero, proving that these are linearly independent. Okay, well, the notation, the y1, 1, y2, 1, y1, 2, y2, 2, let's think about why we did that. We did that to distinguish this column from this column. If we call this y1, y2, and call this y1, y2, it looks like they're the same, and they aren't. So we add an extra subscript. Now, what subscript are we going to add? Well, okay, let's take this solution, which is just this. Okay. Now, this is our big fancy y1 vector. For big fancy y1 equal y1, y2, so that we have a y1 and a y2 to put in this, well, we're going to call y1, instead of calling it y1, and for this purpose, we're going to call it y1, 1. Okay, which means our y1 for our first vector. And we're going to call y2, instead of calling this y2, we're going to call it y2, 1. y2 for the first solution vector. Okay? So this is our y1, y2 for our big fancy y1 vector. And the second subscript indicates it's for this vector. Okay, similarly over here, and don't have room to write this, but we're going to call this function, this is going to be our y1, this is going to be our y2, but this is the y1 that goes with our solution vector 2. So we call it y1, 2. And this is the y2 that goes with solution vector 2, so we'll call it y2, 2. So that makes a certain amount of sense. And it puts our subscripts in the usual order when we try to do our Wronskian. I've got absolute value signs around this matrix. We talked the Wronskian is the determinant. And if you do that determinant, as we said before, I'm pretty sure you get square root of 2 over 2 times e to the 2t. Now I was kind of sure you were going to get an e to the t before, but I put question marks around it. I put smaller question marks around this one. I kind of think I've got it right. But you work it out and make sure. So, okay, what's the big deal here now? Remember that when we did this, we got two eigenvalues, and all this came out of one of our eigenvalues. Now, our eigenvalues were complex conjugates. Okay, since the eigenvalues were complex conjugates, and you can work through the details of why this happens, the two solutions we get here are going to be at least scalar multiples of the two solutions we would get if we evaluated the conjugate. Okay, now you can see just how close those two solutions are. You could work it through for the eigenvalue 1 minus the square root of 2i. Just do everything that we've done here. You can do it in a few minutes. It's not difficult. And it's good practice. And just see how your two solutions relate to these. Okay? But the point is, we have two big fancy y vector, column vector solutions. They're linearly independent, and that's a complete solution to our problem. Okay? So we don't need to go to the second, to the complex conjugate of the eigenvector that we used to get this. And that's kind of neat. So we got two solutions here out of one of our complex conjugate eigenvectors. Now that doesn't work if you don't have complex conjugates. If you have complex conjugates, that's the way it works.